Hi everyone. Thank you all for joining me. My name is Chaki Benita, and I want to talk to you today about unconventional ways to index UUIDs in PostgreSQL. Now, I know that some of you read the title of this talk and think to themselves, oh, this guy's just going to talk about B-tree indexes for 25 minutes. But in fact, I'm going to show you different, hopefully exciting ways that you don't know about to index UUIDs in PostgreSQL. So let me just introduce myself. My name is Chaki Benita, and I am a software developer and technical lead. I'm very much interested in databases, web development, and software design. And this is exactly what I'm going to talk about today. So let's start talking about UUIDs. So UUID stands for Universally Unique Identifiers. These are 128 bits, which are usually represented in hex. This is what a UID looks like, okay? For example, in Postgres, you can use the function gen_random UUID, and this is what you are going to get. So there's many types of UUIDs. 1 and 2 contains the MAC address of the computer that generated them. These are kind of old. You have 3 and 5, which contains some namespace and name, very specific to a specific domain. And then you have UUID 4, which is completely random. Okay, the most popular type of UUID is 4. If you're not sure what you're using, you're most likely using UUID 4. So UUID 4, as we said, 128 bits. So you have 6 bits allocated for the version. You can see that version, the number 4. And then you have another 2 bits allocated for the variant. Aside from these 6 bits, the remaining 122 bits are completely random, okay? So you probably ask yourself, what are UUIDs good for? I mean, why do I really need big chunks of random text? So first of all, because they are big chunks of random text, there's very low chance of collision. This means that we can have client, like our client applications or any edge device, generate unique identifiers, which are most likely going to be unique when we push them to the server. So this is what's called a distributed unique identifier. This can be very useful under many types of circumstances. Another common use case for UUID are public identifiers. And the reason that they are so good is that they are very hard to guess. Now, I'm going to give you an example. Say you have this, I don't know, e-commerce shop, and you have a customer placing an order. Let's say that you give this order the number 5. Now, a sophisticated customer might think that, wait, if there's a order number 5, there's probably going to be order number 6, 7, 8, 9, and 10, right? So this is called an enumeration attack, when someone can guess IDs of objects in your system. Another type of information that sequential IDs reveal that public identifiers such as UUIDs don't is business information. And I'm going to give you an example. Say that I want to know how many orders my competitor is processing every day. I can, for example, wake up in the morning, place an order. I get an order with the number 10. Then the next morning, I wake up, place another order. I get order number 90. Now I know that my competitor processed at least 80 orders during that time. Okay, so this is the type of information that sequential IDs can leak that public identifiers such as UUIDs don't. Okay, so UUIDs come with a cost. They're not all that great. They do have some disadvantages. First, if you saw this big chunk of text, you know that it's not very human or user-friendly. Imagine that you call service center and you want to get like information about your order, and the teller asks you to, can you read the UUID for your order? That's not very friendly. Another downside or disadvantages of random UUIDs, which we are going to talk about in this presentation a lot, is that it's not sortable in any meaningful way. I mean, it's just it's just a random chunk of text, right? So sorting by UUID is not very meaningful. On the contrary, if you imagine sorting by some kind of sequential ID, 1, 2, 3, 4, 5, then it is meaningful because the order is most likely the order which you inserted the rows in, okay? So these are the disadvantages of random UUIDs. So enter sortable UUIDs. This is a type of development that we see in recent years. And we talked about UUID 1 through 4, and there's a new RFC draft for UUID 6, 7, and 8. Now, the nice thing about the new types of UUIDs that they are sortable. I'm going to talk specifically about time-based UUIDs, and I'm going to focus on ULEAD, okay? So let's see what it looks like. So this is a ULEAD. Okay, it looks exactly like a random UUID, but it's built differently. Okay, so if you see the first two chunks of the ULEAD, this is actually the timestamp when the ULEAD was produced. And the other parts of the UUID are completely random. Okay, this makes the UUID sortable in a meaningful way. Okay, so as I insert rows and generate new UUIDs, new ULEADs, they are going to be slowly incrementing, okay? Because the prefix is essentially the timestamp. Now, just to illustrate, let's say that you want to know when I produced this ULEAD, you can actually take the first two chunks of the ULEAD, convert them to big int. This is the number of milliseconds since 1970. And then you can divide by 1,000 to get the number of second and convert it to a date. And then you get that I produced this ULEAD on the 10th of March, okay? So that's what a ULEAD looks like. The advantages of sortable UUIDs as opposed to random UUIDs is that they have potentially good correlation, meaning I can actually sort the table by the UUID in a meaningful way, okay? So just to recap the difference between sortable and random UUIDs, the correlation of random is bad, for sortable UUIDs is good, as well as for sequential IDs. We mentioned that random UUIDs are not very user-friendly, but also the sortable UUIDs because they look like random chunks of text. The sequential ID, on the other hand, is very user-friendly. You can just call and say, I placed an order number 1167. Now, we also talked about leaking business information, and random UUIDs and sortable UUIDs address this issue. Okay, sequential IDs don't. Okay, and also we talked about UUIDs generated at the edge, meaning they can be used as unique identifier, distributed unique identifiers. These are identifiers that can be generated by the client application. So sequential IDs cannot, because you need to coordinate. So that's a recap of UUIDs and sequential IDs. So now that we understand the benefits of UUIDs, let's talk about how you index them in Postgres. So to start off, we are going to set up a table with a UUID. We're using the UUID built-in type in Postgres, and we're using a text field just to make the table a bit big, okay? So this is what it looks like. We are inserting 1 million rows into the table, and we're using gen_random UUID to generate the random UUIDs, okay? We then analyze the table. We get a table which is roughly 1 gigabyte in size, okay? Now, we do it the exact same thing, but this time we're going to do that with the ULEADs. These are the sortable UUIDs, okay? So we are using the built-in UUID type in Postgres because ULEADs are compatible with UUIDs. And once again, we're using a chunk of text to make the table bigger. And we insert 1 million rows into the table. Notice that to generate the ULEAD, I actually provide the timestamp. So I made sure that the timestamp is unique. And we can see that we have 1 million rows. Each is 1 second away from the 1st of January, 2023, okay? And we analyze the table. We get a table with roughly the same size. So now for our benchmark, which we are going to use to try out different indexing techniques, okay? So we have a table. Sorry, we are going to execute 200 queries for UUIDs against this table. 100 UUIDs which exist in the table, and another 100 UUIDs which do not exist in the table. And then we are going to measure the mean execution times in these 200 executions, okay? So to establish a baseline, we are going to run this benchmark with no indexes at all, okay? This is what it looks like. The implementation is not very important. We basically iterate over 200 UUIDs and execute, select star from a table where UUID equals something. And this is an example result. We executed 200 queries, and the mean execution time with no indexes was 179 milliseconds per query, okay? So if we execute a query to search for a row with no indexes, we are going to get a response in roughly 179 milliseconds, okay? So that's the baseline, and we are going to compare everything to this. Okay, so the first index type, B-tree. I know I said we're not going to talk about B-tree, but it is the king of all indexes, okay? So a B-tree index uses a tree structure, okay? If we want to look for a value in a B-tree index, for example, the value 5, we start by scanning the root block. That's the top block in the tree. And then we navigate the root block. The value 5 is between 3 and 7. So we move on to the middle leaf block that contains values between 3 and 7. And then we start scanning the leaf block and compare every entry to the value that we are looking for. Once we find the value that we looked for, in this case, 5, this index entry, which also contains the value 5, also contains a list of all the rows that contains this value, the TIDs of all the rows that has the value 5. Then we can go to the table and get all the rows and do whatever we need with them. This is how a B-tree index works, okay? So let's start by creating a B-tree index on our UUID column. Notice that if you don't mention the type of index that you're using, the default type is B-tree. So if you're not familiar with any type of index in Postgres, you're using a B-tree index, okay? So we just generated a B-tree index on the UID columns in table UID test, and the size of the index is 30 megabytes, okay? Next, we want to check that the index is in fact used when we are trying to fetch a row by UUID, and that's the query. And you can see that the database is doing an index scan on the B-tree IX index, which is the index we just created. And we also can see that it's quite fast. So let's execute our benchmark, and we get a very, very fast timing. That's less than a millisecond, fifth of a millisecond, 0.021 milliseconds per execution on a random UID. And we can execute the exact same thing on a sorted UID, and we get roughly the same timing. That makes perfect sense. So very, very fast. And the index is roughly 30 megabytes in size, okay? All good. So now let's go to talk about some of the drawbacks of using B-tree indexes or different elements of a B-tree index which relates to UUIDs. So first, let's say that we have a sorted UUID, okay? That's the UUID that is prefixed with the time. So when we insert new UUIDs into the table, these UUIDs are prefixed with the current time, which means that they are most likely going to be slowly incrementing, okay? So the rightmost leaf block in the B-tree index contains the maximum value. So as we insert more rows into the table, these rows are most likely slowly incrementing, right? So we place an order right now, and then a second from now, 2 seconds from now, 5 seconds from now, and so on. So as we insert rows into the index, they are most likely going to be inserted to the rightmost leaf block. That's the leaf block that contains the maximum values. So we are always inserting the maximum value. So because we are constantly inserting into the same leaf block at the rightmost leaf block in the index, the database can optimize that, okay? So it can make it better. I don't want to elaborate too much because it's besides the point, but since we have something that like a pattern, the database can optimize that. If we consider, however, the random UID, when we insert data into the index, it's completely random. It's not sortable in any meaningful way. So we are basically inserting data into different leaf blocks in the index, right? You can see that we have this right leaf block, then the purple middle block, the orange on the left, and so on. So because we are inserting data into all different blocks in the index, it's much harder for the database to optimize. So we can say that from an inserting perspective, sortable UUIDs should be a bit better than the random UUID. Another thing that we need to consider when talking about B-tree indexes is that B-tree indexes can actually satisfy range queries. That's queries where we want to find something which is between two values, okay? Search for a range. So when we have sorted UUIDs, which are prefixed by their timestamp, it actually makes sense to search for ranges. In this case, for example, I generated the minimum passable ULID for 2 o'clock on the 1st of January and then 3 o'clock on the 1st of January. And I can actually use the index to satisfy this query. So B-tree index can be used for range queries. So let's just recap on B-tree index before we move on to more exciting types of indexes. So the B-tree index stores the values, the index values in the leaf. This makes the index size affected by the size of the index values. The bigger the values that we are indexing, the bigger the index is going to be. We also saw how inserts of different types of UUIDs may affect insert performance, right? So random UUIDs are scattered all across the leaf blocks, while the sorted UUIDs are concentrated at the rightmost leaf block, and the database can optimize that. We also saw that B-tree index can be used to satisfy range gains, that between, and a B-tree index can also enforce unique constraints, okay? So if you need to enforce unique constraints in your, let's say, OLTP system, then you need a B-tree index, okay? Great. Next up, let's talk about hash indexes, or as I like to call them, the ugly duckling of index types. And the reason for that is that they are wildly unpopular because they were mostly discouraged before Postgres 10. So a hash index uses a hash table data structure, which we are going to see in a second. So to create a hash index, we need to notice that after the using here, we provide the method. In this case, we say that we want to use a hash index on the UUID column. The size of the index is 32 megabytes. And if we execute the query, we can see that Postgres decided to use the hash index that we just created, okay? If we execute the benchmark on the random UUID, we can see that it's very, very fast. We do the same for the sorted UUIDs, roughly the same timing, very, very fast. So fast and just slightly bigger than the B-tree index. So how does a hash index actually works, okay? Let's say that we have these values, A, B, C, and D, okay? And now we want to build a hash index on these values. So the first thing that we need to do is we apply a hash function on every value. And in the slides, you can see the result of this hash function, okay? So A, the value is -201, and etc., okay? Now, we want to divide these values into buckets. So if we have, for example, 2 buckets in our hash index, then we take the value, the hash value, and apply modulo the number of buckets, in this case 2. So now you can see that the value A goes into bucket 1, and B, C, and D go to bucket 0. So this is our hash index. Congratulations, you just built a hash index in Postgres. So if we want to use our hash index to find something, we do the exact same process. Say we want to find the value B. We first apply the hash function on the value B, we get the hash value, then we apply modulo the number of buckets and find the bucket, in this case, 0. Then we go to the index, get all the row pointers in the bucket 0, 2, 3, and 4 in this case, and these are the rows that we need to fetch and scan from the table. So a hash index, just to recap, a hash index is ideal for high cardinality data, okay? What this means is that if we have a lot of repetition in the table, then a hash index would not perform very well because all the values are going to map into the same buckets, okay? So we want to use a hash index on mostly unique values. Another very nice feature of a hash index is that it's not affected by the size of the indexed values. Remember, a B-tree index stores the values in the leaf blocks. A hash index only stores hash values. UUID is a very big data type, so using a hash index on a UUID makes sense. Hash index also comes with a few limitations. First of all, because we're not storing the values, we can use a hash index to enforce a unique constraint. We can use it for sorting, and we can use it for range scans. Okay, if you need range scans, don't use a hash index. Okay, so now, if you know me, even for a little bit, you know that I'm a big fan of block range indexes. So I want to present, and this is kind of unexpected because you would not expect a BRIN index to appear in a presentation about UUIDs. So a BRIN index, block range index, indexes a range of adjacent pages, okay? And there's various methods to do it. So before I'm going to explain the methods, let's just go into see what it looks like. So we want to create a BRIN index on our UUID column. And we are going to talk about these pages for ranges in a sec, okay? In this case, I'm using the default min max ops, and you can see that the size of the index is just 3.5 megabytes. Remember, the hash and the B-tree indexes were more than 30 megabytes in size, but the B-tree index is much, much smaller. So if we want to check if the index is actually used, we execute a query and we can see that the index is used, but it's very, very slow, okay? So we created a B-tree index, a BRIN index on our random UUID, and the index was used, but the query is very, very slow, okay? And if we execute the benchmark, we can see that the default is 530 milliseconds per execution. And just to remind you, the B-tree in the hash was less than 1/5 of a millisecond. So that's a huge leap in performance. So to understand why this happens, let's see how a BRIN index actually works, okay? So let's say that we have these values, 1 through 9, each in a single page, okay? So first, BRIN index takes these pages and divides them into ranges of adjacent pages. In this case, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the ranges. Now for each range, we keep the minimum value and the maximum value. So this is our index, okay? Say that we want to search for the value 5 in our BRIN index. We look at the first range, 1 through 3. We know that 5 is definitely not inside this range, okay? So we can skip these rows. The second range, 4 through 6, 5 might be here, okay? Notice that I'm saying might be here, not necessarily here. And finally, 7 through 9, definitely not here. So now using the index, we can we know that we only need to scan blocks 4, 5, and 6, and we don't need to scan block 1, 2, 3, and 7, 8, 9. Okay, so this is what a BRIN index works with the min-max ops. Now, what if the values in the column are not sorted like 1 through 9? They are not sorted, they are jumbled, okay? So let's do the exact same process. Take groups of 3 adjacent pages and keep the minimum and the maximum. This is our index, and we are going to use this index and try to search for the value 5. So now we look at the first range, 2 through 9, 5 might be here. 1 through 7, 5 might be here. 3 through 8, 5 might be here. So essentially the index is useless. We were unable to reduce our search in any way using the index, okay? So this is a good time to mention correlation. Correlation is a metric maintained by the database that keeps track on the correlation between the physical row ordering and the logical row ordering of the column values. So to understand, if we look at the value of correlation, the statistics that Postgres maintains on our columns, okay, we can see that the random UUID has zero correlation, meaning there is no correlation between the actual value to its position, physical position in the disk. However, for the sorted UUIDs that is constantly incrementing, we have perfect correlation, okay? So in the first block of the table, we find the minimum value, and in the last block in the table, we'll find the maximum value, okay? So this is very meaningful when we are talking about indexing. So just to illustrate, let's create a Brin index, but this time on the ULID, on the sortable UUID. And let's see how it performs in our benchmark. First, we can see that it's used, and if we execute the benchmark, we can see that now we get a significantly improved timing. We now get 12 milliseconds per execution, okay? That's a huge leap. So the random with the min-max ops got us 530 milliseconds, and on the sorted UUID, we got 12 milliseconds. That's a huge leap, okay? So 99% of the developers would stop here. But there is something we can do about this random UUID. There is a way we can use a Brin index for the random UUID. This is where a very exciting new feature in Postgres 15 comes in very, very handy, and that's the Bloom operator class for Brin index, okay? So to understand how this works, we need to understand what's a Bloom filter and how it works, okay? So a Bloom filter is a very, very space-efficient data structure that can answer the question, is this value in the filter? Now, the answer is either definitely not, just like the min-max before, or maybe. Not yes, but maybe. So let's build a Bloom filter. Let's say that we start with an empty filter of size 10. So each value here represents a bit in the filter. So we have no value, so everything is 0. Next, we want to insert the value A. So the way Bloom filter works is that you apply multiple hash functions on the value, and then you apply modulo on the size of the filter to get a bit. In this case, we need to turn on bit 2, 6, and 9. And you can see in the Bloom filter below that we turn on the bits that correspond to each value. If we want to insert the value B, we do the same process. We apply the hash functions on the value B, modulo 10, which is the size of the filter, and we turn on bits 1, 7, and 9. Notice that bit 9 was already turned on. So now we have 5 bits which are turned on in our filter. So let's try to search for the value C in our filter. So we do the exact same process. And so we are going to do the exact same process. We are going to apply the hash functions on the value C, and then we look at the corresponding bits in the filter. We can see that the bit 1 is turned on. That's the first green one. And then we can see that bit 3 is turned off, which means that the value C is definitely not in the filter. Okay, so using the Bloom filter, we know that the value C does not exist in the table, so we don't even need to access any of the rows. If we do the same for value D, we apply the hash functions, we find bit 2, 7, and 9, okay? And then we check the filter, all the bits are turned on, so the value D might be in the filter. Now, we know that it's not, but according to the Bloom filter, it might, okay? So if you're interested about the specifics of the implementation, I highly recommend reading the source. It's very, very informative, seriously. So now just to complete our example, we create a Brin index using the Bloom ops, okay? Previously, we used the min-max ops. Now we are going to use the UUID Bloom ops, okay? This is what it looks like. And notice that the size of the index is bigger, almost twice the size of the Brin index using the min-max ops. Now let's try to use this index, and we execute the query. We can see that Postgres uses the index. Next, we execute the benchmark on our random UUID, and look at that, 15 milliseconds. That's a huge leap for what we saw before. That's 40 times faster than the Brin index with the min-max ops on the random UUID, okay? So just a note about Brin index maintenance. A, it's not updated by default with new data. That's a bit surprising, I know. This means that the Brin index is mostly useful for data that is not changing very often, meaning data warehouse environments and so on. You can configure Brin index to update on every vacuum. Check out the auto summary option. And you can update it manually using this function. So finally, it's not Brin index, not ideal for data that updates very frequently. You can actually control the size versus accuracy with the size of the range. We used in our examples 2 pages per range or 3 pages per range, but the default is 128. The bigger the range, the smaller the index, but less accurate, okay? So use the min-max for columns with high correlation. You can use the Bloom for low correlation columns like the random UUID. And there's actually other operators which are very exciting, like multi-min-max for high correlation with outliers and so on. Worth checking if you're interested about Brin index. So just to summarize everything, we can see that B-tree and hash produce very large indexes, but very, very fast execution times. We can see that Brin indexes produce small indexes and produce somewhat fast-ish, I would say, execution times, which sometimes it's enough. You know, you don't have to every query to be super fast. Sometimes you just want to save some storage, okay? So takeaways from this talk. First, B-tree and hash, fast, but produce big indexes. Hash can outperform a B-tree index. This is what we saw in our example. The hash was faster than the B-tree for fetching single rows by UUID. Brin is small and fast, but not as fast as hash or B-tree. And we saw that Brin offers multiple ops for different types of columns. So min-max for high correlation, Bloom for low correlation, and other ops which you can read about yourselves. And finally, which one should I use? So obviously it depends, and I can map all the possible needs. But generally speaking, if you need to enforce a unique constraint, there's no other option. You have to use a B-tree index. That's correct for most OLTP systems. Second, if you don't need to enforce a unique constraint and you have data that is not accessed or updated very frequently, okay, you can use a Brin index, either Bloom or min-max, depending on the correlation. If you do have something that accessed a lot and you need range queries, use a B-tree. High correlation column, use a hash. Otherwise, choose whatever works for you. But hopefully you now know that there's more option than just a boring B-tree index. So that was very fast, and hopefully you learned a few new tricks from this presentation. If you want more like this, then check out my interactive class on Educative, or you can join the online live training I give in O'Reilly. It's 3 weeks, very cool. I also write a lot, so you can check any of these articles on my website, and you can find me on my blog, on Twitter, on LinkedIn, or just send me an email. I don't know, just say, hi, Aki, watch your show on Citrus, and it was great. So thank you very much. I hope you enjoyed this talk.